AS Applied Maths Statistics, Chapter 5.5, Tree Diagrams. Another diagram that we can use instead of a Venn diagram, and it is really useful when you're trying to repeat events, so whether it's tossing a coin or whether it's rolling a dice, picking a card out of a pack, etc. When you're doing repeated events, then a tree diagram is the one to go for. When you've got set probabilities, then the Venn diagram is the one to go for. So if we just have a look at example 5.5.1 and set a tree diagram up for this situation. Now it might be that some of you can do this without tree diagram, but just like a sample space, just like the Venn diagram, it organises the probabilities and makes questions so much easier. So when I have two things, so I'm getting two cards out of a shuffled pack of ordinary playing cards. That means that is without replacement if I'm dealing two cards. Then I want to set a tree diagram up that looks something like this. So I am using so we're going to let A be the event that we select an ace. And like I've said before, defining that early on in the question just means now that I can use a notation. I'm using A' to represent not getting an ace. Now I don't want to set this up as getting an ace, getting a king, getting a queen, because there'd be just too many branches to it. So I'm literally going for ace and not ace. And it just needs to be a quick diagram in order to help me organise my ideas. So this first bit here is card 1. And then we've got here the second one, which is card 2. I was thinking about if you're starting at this point here and you're either going to go that route or that route. So when I select the first card, if I get an ace, well, there are 4 aces in a pack and there are 52 cards in total. You are expected to know about playing cards for statistics questions. So you might need to just brush up on a pack of playing cards. So then if I'm going this route, once I've picked an ace, for my second card I would only have 3 cards left in the pack and there's only 51 cards in total. Or from that point of picking an ace, I could end up taking this route where I don't get an ace the second time, but I still have the 48 cards available to me. So there's 48 cards that are not an ace, but it's still out of 51. Coming back to the beginning, and probably makes more sense to fill this one in first because it's ace and not an ace, so these two branches are mutually exclusive. So a tree diagram organises this into mutually exclusive events. These are not going to happen at the same time. If 4 of the playing cards are an ace, then that means 48 of them are not. So that ends up being 48 out of 52. If I've taken this route here, so I've not an ace the first time, then I will have used one of those, so I've got 47 of them left and that's out of 51. But if I've come this route, when I've got to not an ace, I must have 4 aces still remaining. And what you should be checking at all points is that your branch adds up to 1. So you need to be checking that the sum of each branch is 1, and that's the same with each of them. So you should have a sum of 1. So 47 and 4 need to be 51, 48 and 4 need to be 52. So you check that you have a sum of 1. Now what we can do with a tree diagram and what makes it easier is when we're working the probabilities out, if I travel across the tree diagram, then I can multiply. When I travel down the tree diagram, then I can add. Now the multiplication comes from independent events, and these are not necessarily independent events, and in the second year we look at this in a lot more detail. So it's called conditional probability, and when we have written these probabilities onto these second branches for card 2, we have taken into consideration what has happened in the first situation. So we're applying what we call conditional probability to it. Now we'll look at the formulas in the second year of the Applied Maths Statistics course. So you are allowed to just accept that you are multiplying, but it is really important that you don't see this as having independent events. They are only being treated as such because we have already considered, when we worked out this 3 over 51, we've already considered what happened in the first situation and what effect that had on the second situation. However, going down, these are most certainly mutually exclusive. If I travel from this starting point and I get an ace for the first card and an ace for the second card, that cannot happen at the same time as getting an ace for the first card and not an ace for the second card. Those two events are mutually exclusive. So what we have here is that we'll be getting two aces, that will be getting an ace and then not an ace, this will be getting a not an ace and then an ace, and this last one will be getting two not aces. That is the same as doing a sample space. So if you think right back to the first video that we did on this, or the start of this chapter, you can do a sample space by saying, well, the first card is A, not A, the second card would be A, not A. Well, what combinations do I have? Well, I can have two A's, I can get an A and not an A, I can get not an A, and I can get two not A's. So that's all the different combinations. But where a tree diagram is better maybe than having this situation here is that it's taking into consideration the different probabilities. The sample space is really good when we have even probabilities of A and not A happening, but a tree diagram is more useful when the probabilities are different, as they are here with the 4 and the 48. Okay, so that's how the tree diagram works, and hopefully you already knew all that anyway, so it's just revision. So find the probability that at least one of the two cards is an ace. So thinking about the different combinations, if at least one of the two cards was an ace, it would be that one, and that one. At least one of them is an ace. Now I can see a shortcut here. Rather than working out all of this, so to get this one here, just to clarify, we would do that, and then for this one we would do that, and then we would add all of these three together once I have done the multiplication. Notice that these two, if we were when we're multiplying fractions, we multiply numerator and denominators together. So this one is 4 times 48 over 52 times 51, which is the same value as 48 times 4 over 52 times 51. It's just taking into consideration that you've got more chance of this happening because there are two possible ways that you can get an ace and not an ace. So you do get the same probability, it's just organised differently. But what I'm spotting here is that I can take a shortcut, and that is by working out this bottom one, which is the one I don't want, but because it is the only one I don't want, it means that I can subtract it away from 1. So the probability of getting at least one ace is equal to 1 minus the probability of getting not ace, which is going to be the easiest way to do that calculation. So we can take off that multiplication there, which is equal to 33 over 221. So that's my answer there. Okay, so you can do it by adding those 3 purple ones together, but obviously in an exam it would be a lot quicker to do this. And it might be, if you're not asked for a tree diagram, it might be that you just sketch out the tree diagram and then just fill in the bits of the probability that you're going to be working with and use it as kind of a tool for calculating it. It just helps you organise your results. So looking at this example, we have got a bag that contains 7 green beads and 5 blue beads. So I have 12 beads in total there. A bead is taken from the bag at random and it is not replaced. So we've got a not replaced situation here. And we need to apply that to the tree diagram. So pause the video, have a go at filling in the tree diagram, and then have a go at the questions and just check in to see if you've got the right answer. So we have 7 green beads in the bag and there's 12 in total, and I have 5 green beads in the bag. There are 12 in total. 7 and 5 make 12, so I know that that's adding up to 1. If I come along the route that's green, so if I get a green the first time, then that means I have 6 left and I have 11 in terms of the number of beads in the bag. I still have 5 blue beads out of 11, and 6 and 5 makes 11. If I choose a blue bead the first time, then I have 7 green beads still left out of 11 because I've used one of the beads, and now blue has gone down to 4 out of 11, and 7 and 4 makes 11. Therefore, the total there of those fractions is 1. Probability that I get a green and a green. So I can just multiply. Remember, we can multiply working across a tree diagram. So we have got 7 out of 12 times 6 out of 11, which is equal to 42 out of 132. I can multiply them. These are not independent events, but because I have considered what is happening in the first situation when I have calculated this 6 out of 11 onto my tree diagram, it means that I can multiply across. In terms of that fraction, I can just simplify it down to get 7 out of 22. Probability the beads are of different colours. So if I'm doing the probability that I get 2 different, that means that we have got the probability that we get a green and then a blue, or we get a blue and then a green. So I'm going green and then blue, so I'm going along that route, or I'm coming for blue and then green, so it's that one there. Now these are mutually exclusive, so I'm multiplying going across because I've taken into consideration the fact that I've selected a bead, but getting green and then blue, so getting green on the first one followed by a blue on the second one, cannot happen at the same time as getting a blue on the first one and a green on the second, so I am able to add them. Remember, we add going down a tree diagram. So we have got 7 out of 12 times 5 out of 11 plus 5 out of 12 times 7 out of 11, and as you can see, the numerators are the same, the denominators are the same, it's just being multiplied in a different order, so both of those would get us to 35 out of 132. So you can take shortcuts if you understand how the probabilities work, and you can take shortcuts in calculations, but it's important that you understand exactly what is going on, and therefore if you find this difficult, the best thing you can do is draw your full diagram out. Okay, so final example, pause the video, have a go at the question, draw out your tree diagram, and then check in and see if you've got the right answer. So here's our Venn diagram. We have got 3 yellow and 2 green. So the first one is 3 over 5, 2 over 5. Then when we've chosen a yellow, we're now down to 2, and we've got 4 left to still have 2 green. They add up to 1. I've chosen a green, so I still have 3 yellow, but I've used a bead, so I'm down to 4, and I've used one of the greens, so I've got 1, and I check that they add up to 1. Probability that they are of the same colour, which means that I can have either probability that I get yellow yellow, or the probability that I get green green, and they are mutually exclusive, so I can add those together. So we've got 3 out of 5 times 2 out of 4 plus 2 out of 5 times 1 out of 4. So when I calculate that, I get 8 out of 20, which is 2/5. Probability they are different. Well, I could work this out by doing yellow green and then green yellow, or I could say, well, that has to just be, it's completely mutually exclusive to being the same. So if the probability that they're same is 2/5, then the probability that they are different has to be 1 minus 2/5, which is 3 over 5. So I'm going to take a shortcut if I can see one, but you are correct to do 3 out of 5 times 4 out of 5, 3 out of 5 times 2 out of 4, add 2 out of 5 times 3 out of 4.